Good afternoon, children. Good afternoon, children.
Good afternoon.
Good afternoon. How many of you completed the assignment that I had posted on WhatsApp? Give out your names. Sangamitra finished, is it?
Yes, ma'am.
Very good. Who else? Tarun Ishwaran, Pranav Rajan, Hitesh, Deepika, okay, Vasudevan. What about Nikita? Satvika and Tarun? Satvika? Tarun? No, only Sangamitra has finished. Excellent, Sangamitra. I'll share the complete steps on WhatsApp. I'll just hear the answers from you. So Sangamitra, what's the answer for the first one? That is the material was it had the heading test 6.
Yes.
Yeah, what's the answer? Answer for the first one?
108.
108. What's the value of x square plus y square plus z square?
35.
35, very good. And the value of x cube plus y cube plus z cube minus 3xyz is 108. Correct. Correct. Very good. Oh, it's not this material, but. Yeah, the answer for the second one, Sangamitra.
Two a plus b plus 2 the whole square.
2a plus b plus 2 the whole square. Very good. Expand, Sangamitra, expand a cube plus b cube plus c cube minus 3abc. A cubed plus b cubed plus c cubed minus 3abc.
The same question.
No, I'm asking you to complete the identity. A cubed plus b cubed plus c cubed minus 3abc is equal to
A square plus b square plus c square plus 2ab plus 2bc plus 2c.
No, complete this identity, class. Complete this identity. What is a cubed plus b cubed plus c cubed minus 3abc? Complete this identity is equal to.
Which identity? A plus b plus c into a square plus b square plus c square minus ab minus bc minus c.
Yeah. All right. So in this material, question number 3 is a proof. So you have to prove that this expression is 0. Tell me the answer for the fourth one. P cubed minus Q cubed. What's the value of P cubed minus Q cubed? Sangamitra.
5050 by 2, 729.
Correct. 5050. 5050 by 729. Perfect. In question number 5, what is the value of 2x plus 3y? In question number 5, what is the value of 2x plus 3y? You didn't try that, is it, Sangamitra?
Is it 1000?
2x plus 3y, the whole cubed is 1000. What is the value of 2x plus 3y?
10.
10, right. And the factors for the last fifth one, the alternate question, fifth one.
X plus 4 root 3 and x minus 2 root 3.
Very good. Excellent, Sangamitra. X plus 4 root 3 and x minus 2 root 3 are the factors of the given expression. Good. Class, take a screenshot. These are the answers to the questions which I posted. Please take a screenshot. All of you. Should I show it again? I'll come from behind.
Yes, ma'am.
You want it again? Okay, this is the first one. Too many second side. All right.
Ma'am, can you show me the fourth question?
Fourth question, is it? Yeah. This one? Pranav, this one?
Ma'am, yes, ma'am. Just one only, ma'am. 1 minute, ma'am.
Done, Pranav?
Yes, ma'am. Done, ma'am.
Okay. Were you asking for this one? Did you ask for this one?
Ma'am, yes, ma'am.
Okay.
Yeah. This material I had not sent completely. You can take a screenshot now. of these, I had sent the last one, sixth one, 6A and B. Now this is the first chapter, real numbers or number systems and polynomials together. So let us see, this is polynomial. So this is for term 2. This is term 2. This is term 2. This one is term 1. This is from the chapter number systems. This is also number systems. This is number systems, not for term 2. Term 2, term 2. Yeah. So except these three. 3A and B, 2B. These form a part of term 1 syllabus, so you can ignore those questions. You can try the others. So since only Sangamitra has worked, I have to ask her. What's the answer for 6B, Sangamitra? What are the possible expressions for LBH?
2x plus 1, 2x minus 1, 2x plus 3.
2x plus 1, 2x minus 1. 6. Yeah, 2x plus 1, 2x minus 1, and 2x plus 3. Okay. Okay, this one, it has another side, the questions. Children, take a screenshot. These are the questions on the next side. So again, this one is term 1. Ignore this, ignore this. These two you can try. Factorize using factor theorem. Factorize using factor theorem, and the other one is also a part of polynomials. Yeah, now I'll show you all the answer slides. I'll give you sufficient time, children. I hope you don't have to request me to show them again. Yes, this is the first one. Please take a picture. So the answer for the first one, 6A, I had posted this question. So since a square minus 3a, you find this expression in more than one place, a square minus 3a. A square minus 3a, a square minus 3a. So let a square minus 3a be x. So rewrite this. This is x, so x square minus 8x minus 20. x squared minus 8x minus 20. Let's assume a square minus 3a to be x. You can call it y or z. So rewrite the given expression in terms of x, y, or z. So you have this. Now factorize as usual by splitting the middle term, and that brings you to this step. Factorizing by splitting the middle term, split the middle term, grouping, and here are the factors. Now once you're done, so this is the end of factorizing. This is the last step in factorizing by splitting the middle term. So now that you come to the end of it, you have to put it back. What is x? A square minus 3a. So in place of x, a square minus 3a. In place of x, a square minus 3a. But you see that these two factors are again quadratic. These two factors, when you look at this and this, they're again quadratic. They're again quadratic. So which means you can try to factorize them further. In case they can be broken down into two further factors, you can do it. So we have to try that. Try by splitting the middle term. If you're able to find two numbers that satisfy the sum and the product, you can factorize. Sometimes you may not be able to factorize it. So in that case, you can leave it. You can leave it quadratic. So try to factorize by splitting the middle term. And in both the cases, you're able to find two numbers that satisfy the sum and the product. Okay, in both. So you're able to split the middle term. So then you know the procedure. Once you split the middle term, grouping, and then this one. So these are the four factors of the given expression. These are the four factors of the given expression. These are the four factors of the given expression. Dimensions of the cuboid, again, you'll have to factorize. Here we were able to fact 6b. I'm talking about 6b. 6b, the given polynomial is a cubic polynomial. You can try to factorize by grouping. If that does not work, then you have to factorize by using the factor theorem. So to factorize using factor theorem, you'll have to find one factor. You'll have to find one factor and then divide the given polynomial by that one factor to find. So that will give you the quotient. You'll have to factorize the quotient to find the remaining two factors. So first we try, this is a cubic polynomial. This is a cubic polynomial. We'll try to factorize it by grouping. We'll try. If that does not work, that is if you don't get the same expressions in the bracket here and here, if you don't get the same expression, then you can try by rearranging the terms. If that does not work, you can factorize by you can factorize by using the factor theorem. Or supposing you forget to try this, you can always factorize it using the factor theorem. That will always work. This method may or may not work. That is factorizing by, what is this? Okay, so factorizing by grouping may or may not work, but you can always factorize using the factor theorem. So here it just works. The first two terms have 4x squared common. You know that, factorizing by grouping. So grouping the first two terms and the last two terms. Yeah. So taking out the highest common factor, So once you group and factorize, these are the two factors. But you can see that this is a linear factor. 2x plus 3 is a linear factor. 2x plus 3 is a linear factor. Linear, power is 1. But this is a quadratic factor, power 2. So you should try to factorize this further. And that's of the form a squared minus b squared. So a plus b into a minus b. This is of the form a squared minus b squared. A squared, see here, a squared minus b squared. 2x the whole square minus 1 the whole square. This one is of the form a squared minus b squared. 2x the whole square minus 1 the whole square. So a plus b into a minus b, and this one as it is. So the possible dimensions of the cuboid are LBH. So if this is the length, this can be the breadth, this can be the height. You can write it in different ways. So you can see two such ways here. If this expression is the length, then this expression is the breadth, and this expression is the height. If this expression is the length, then maybe this can be the breadth and the other one the height. So you can even say this. If this is the length, then this is the breadth, this is the height. Or if this is the length, this can be the breadth and this can be the height. So like that. So these are, so you can just mention 2 or 3. These are the possible dimensions the cuboid can have. And then the question is to verify. Find the possible expressions for LBH that we answered. So to answer that, you will have to factorize the given, because that's the volume of the cuboid. That's the volume of the cuboid. The given expression represents the volume of the cuboid. We need to factorize that expression to find the 3 factors so that you can assume them to L, B, and H. So we have answered that part. We found the expressions. Find the possible expressions for L, B, and H of the cuboid. So we found the possible expressions for L, B, H. Now we need to verify the result. Whatever result we've got, we need to verify that when x is 5, when x is equal to 5 units. So when verify means you should check if the LHS is equal to the RHS. That's all. That's what verification means. Verification means there is some LHS, there is some RHS. You need to fix that value to x in the LHS and RHS and see to that you get the same answer. That is what is verification. Verification is working one thing, working another thing, and then showing that both the answers are the same. So here when we factorized this, when we factorize this expression, we get 2x plus 1. See, when you factorize this expression, you get 2x plus 1 into 2x minus 1 into 2x plus 3. So this is the left hand side. This is the right hand side. In the left hand side and right hand side, in place of x, we should work it separately. In place of x, you should use the value 5. Work the LHS separately, and here also RHS also work it separately. Work it separately. So you will see that the volume, this expression represents the volume, right? You will see that the answer is the same in the LHS and RHS, so you're verified. You have verified that these 3 are the factors of the given expression. Or you verified that this length, this breadth, and this height gives us the given volume. You verified that this length, breadth, and height can give us the given volume, that expression x 8x cubed plus 12x squared minus 2x minus 3. Verification is basically working the LHS, working the RHS, and showing that the value in the LHS is equal to the value in the RHS. Yeah, so you can see I've mentioned it here. To verify that this expression is equal to the product of these factors. To verify that this expression is equal to the product of these factors when x is equal to 5. So work the LHS, work the RHS, you get the same value, so you verified. All this is not required, children. 7AB. You can take a screen. I don't know. You don't have time to study the given portion, so I think that you're not going to. Yeah, this one, 8A. 8A. Take a picture of this one, 8A. So in 8A, you can see how to factorize using factor theorem. We find one factor, we find another factor, we find the product of the two factors here. How do we factorize using factor theorem? So we need to factorize this. What do you call this polynomial? What's the special name? What do you call such a polynomial?
Quantic polynomial.
Sorry?
Quantic, ma'am.
Okay, or
Biquadratic polynomial.
biquadratic polynomial. How do you factorize the biquadratic polynomial?
First, we need to find a factor by factor theorem, ma'am.
Okay.
And then we have to do it by long division, ma'am. The factor should be divided by the long division.
Only one factor?
No, ma'am, two factors.
You have to find two factors. So what are the two? What are the two roots you see here on the screen? What are the two roots of the given polynomial?
X plus 1 and x plus 2, ma'am.
No, what are the roots? They are the factors. What are the roots? Okay. No. You wouldn't understand that term in instant. Okay. -1 and -2 are the roots. The corresponding factors are x plus 1 and x plus 2. Okay, you're right, Kanishka. X plus 1 and x plus 2 are the factors. So we have found two factors. For this biquadratic polynomial, which has 4 factors, we have found 2. By using the factor theorem, we have found 2 factors. Since p of -1 is 0, x plus 1 is a factor. If this polynomial is made up of y, supposing it is 2y to the power 4 plus y cubed minus 14y square minus 19y minus 6, then you must say that y plus 1 is a factor. Y plus 1 is a factor. So depends on whatever variable is used. If it is z here, it will be z plus 1 is a factor. So here, since a polynomial is an x, x plus 1 is a factor of p of x. And p of -2 is 0, so x plus 2 is a factor of p of x. Next, we need to multiply these two factors, x plus 1 into x plus 2. So like for 75, 3 is a factor of 75. 5 is a factor. 5 into 3, 15 also is a factor of 75. This is a factor of p of x. This is a factor of p of x. So the product, this one also will be a factor of p of x. So divide p of x by this quadratic factor, So it will give you a quadratic quotient. The quadratic quotient has the remaining two factors. This one has the remaining two factors. From this, we already got two. The factors of this expression are x plus 1 and x plus 2. X plus 1 into x plus 2 is this one. Here we have two factors. So the remaining two factors are here. So by applying the division algorithm, this is the dividend. Dividend is equal to divisor into quotient plus the remainder. We know that. Dividend is equal to divisor into quotient plus the remainder. Division algorithm. Dividend is equal to divisor into quotient plus the remainder. But here the remainder is 0. So dividend p of x is equal to divisor into quotient plus remainder because it's plus 0. So this we already know the factors are x plus 1 and x plus 2. Here we factorize by splitting the middle term and we find the remaining two factors. So these are the 4 factors. These are the 4 factors of the given biquadratic polynomial. Take a screenshot, children. only. All right. Continuing with circles. Example 6, circles, example 6. Prove that the quadrilateral formed, if possible, because if ABCD is a rectangle or a square, no quadrilateral will be formed in the middle. So prove that the quadrilateral formed, if possible, by the internal angle bisectors of any quadrilateral is cyclic. Prove that the quadrilateral formed by the internal angle bisectors of any quadrilateral is cyclic. So here we have a quadrilateral. We have taken the quadrilateral ABCD, quadrilateral ABCD. Internal bisectors. So the bisector of angle A. This is the bisect. AD is the bisector of angle A. Sorry, AP. BP is the bisector. See, the bisectors actually, I've trimmed the bisector. So it's like this. The bisectors are like this. Let me show you again. See, when you construct the bisector of this angle like this, you know, so it's like this. This is a line or a ray. It goes like this. So this one is the bisector of angle A. Similarly, when you bisect angle B, this is the bisector of angle B. Now the bisectors, they intersect here at P. So I've just trimmed all this, not shown these pieces, these portions. Similarly, angle C, bisector. This is the bisector of angle C. And this is the bisector of angle D. The bisectors of angle C and D meet at R. So I've trimmed all this. This one is trimmed. That's how we have a figure like this. So we'll say that the bisectors of A and B, the bisectors of angle A and angle B meet at P. The bisectors of angle C and angle D meet at R. These are the internal angles. So the internal angle bisectors. These are the internal angles. Angle A, angle B, angle C, and angle D are the internal angles. Internal angle bisectors. So we have bisected the internal angles. We have bisected the internal angles. When we bisect the internal angles, the bisectors, they form a quadrilateral in the middle. We need to prove that this quadrilateral is cyclic. Any quadrilateral ABCD, see here, prove that the quadrilateral formed by the bisect, any quadrilateral formed in the middle, and this is any quadrilateral. So ABCD is any quadrilateral. Angle A, angle B, angle C, and angle D are the internal angles. The bisectors of angle A and B meet at P. The bisectors of angle C and D meet at R. Now the bisectors of the internal angles of the quadrilateral ABCD form a quadrilateral in the middle. The bisectors, they enclose a quadrilateral. The internal angle bisectors, they enclose a quadrilateral. We need to prove that this quadrilateral is a cyclic quadrilateral. So we know the property of a cyclic quadrilateral. If the quadrilateral is a cyclic quadrilateral, then the opposite angles are supplementary. If you can prove that one pair of opposite angles is supplementary, If you can prove that one pair of opposite angles is supplementary, then the quadrilateral is a cyclic quadrilateral. So we'll do that. What we'll do here is we'll prove that, see, you can prove that angle S plus angle Q is 180. You can do that. What I've worked here is prove that angle P plus angle R is 180. You don't have to find the measure of angle P. That's not possible. You cannot find the measure of angle P. You cannot find the measure of angle P. You cannot find the measure of angle R. But here we're trying to show that angle P plus angle R is 180. See here, PQRS is the quadrilateral. PQRS is the quadrilateral. So the opposite angles are angle P and angle R, and then angle Q, angle S. So we are trying to prove that angle P plus angle R is equal to 180. One pair of opposite angles supplementary, so the quadrilateral is cyclic. You cannot find the measure of angle P or measure of angle R, but we're trying to prove that their sum, whatever be their individual measures, their sum is 180. So the quadrilateral is cyclic. So let's find the measure of angle P. The measure of angle P can be found from the triangle. Measure meaning an expression for the measure. You cannot find the measure. You cannot find the magnitude of angle P. An expression for the measure for the magnitude of angle P. So we have angle P in triangle APB. We have angle P in triangle APB. APB in this triangle. We have angle P. So the measure now this one, see, this is the triangle. This is a triangle. Okay. Now this one is angle A. This is half of angle A because it's bisected. And this is the other half of angle A. This is angle B. This is half of angle B. And this one is the other half of angle B. Because it's bisected, the angles are bisected. So in triangle APB or in triangle ABP, you have half angle A, you have half of angle A, you have half of angle B, you have half of angle B. So what will be the measure of angle P? 180 degrees minus half of angle A minus half of angle B. That's what you see here. That's what you see here. In triangle APB, please don't read ahead. We'll do it together. Don't read ahead. In triangle APB, angle APB is equal to 180 minus the two angles. This angle, and this angle. Half of angle A and half of angle B. Similarly, so like this, we found the expression for angle P. For angle P, we found the expression. Angle P is nothing but 180 minus half angle A minus half angle B. Okay. Next is to find the expression for angle R. Angle R is in triangle DCR. Angle R is in triangle DCR. So as you see here, angle D is bisected. This is half of D. This is half of D. Here, half C, half C, half C, because angle C is bisected. So in triangle DCR or in triangle CDR, we have half of angle C, half of angle D, and angle R. See here, DRC, this triangle. In this triangle, the three angles are angle R, this one, angle R, half of angle D, and half of angle C. So in triangle, you can call it DCR, DRC, you know that. So in triangle DRC, angle DRC, this angle DRC is equal to 180 degrees minus half of angle C and half of angle D. Half of angle C, half of angle D. So like this, we found the expressions for this pair of opposite angles P and R in quadrilateral PQRS. Now, next, let's find their sum because our interest is to prove that their sum is 180. So now let's find the sum of these two angles. Angle APB plus angle DRC is equal to, so add the LHS, add the RHS. Add the contents in the LHS and RHS. So when you add the expressions in the RHS, we have 180 plus 180, which is 360. And then minus half angle A, minus half angle B, minus half angle C, and minus half angle D. this one, all these. Adding, no, so the signs won't change. 180 plus 180 is 360. 360. This one plus this one. So what are we doing? From one triangle, we found angle P. From another triangle, we found angle R. Now we're trying to add the two. Angle P plus angle R. Because we have to show that their sum is 180. So that's what it is. Find the angle P from one triangle, find angle R from one triangle, and add angle P and R. Add angles P and R. So 180 and 180 is 360, and then all this. Now half is common everywhere. So 360 minus half, you can understand this. Angle A plus angle B plus angle C plus angle D. It becomes plus now because we have taken out minus half common. Minus into plus will give you minus. Now angle A plus C. Angle A is the full angle because when you said half of angle A, half of angle A, you meant this full angle A. You meant this full angle A. When you said half of angle B, this is half of angle B and this is half of angle B, you meant this complete angle B. You meant this complete angle B. So here angle A plus B plus C plus D means angle A plus angle B plus angle C plus angle D. We know it's 360. We know that the sum is 360. So 360 minus half, the angle A plus angle B plus angle C plus angle D is 360. And half of 360 is 180. 360 minus half of 360 is 180. So 360 minus 180, which is 180. So we proved that in quadrilateral PQRS, that middle one, okay, this quadrilateral. In this quadrilateral, we proved that one pair of opposite angles, P and R, is supplementary. Therefore, PQRS is a cyclic quadrilateral. Therefore, PQRS is a cyclic quadrilateral. We don't have time to write in this class, children, so please take a screenshot. Done?
Yes, ma'am. Yes, ma'am.
So if you want to prove that you can find, if you want to prove that this angle plus this angle is 180, what you have to do is you'll have to find angle S from triangle ADS and find angle Q from triangle BCQ. You will have to find this angle and this angle from these two triangles. You'll get the same thing, similar thing you'll get. Not the same thing, you'll get similar thing. So you will get this one is, tell me, what will you get here? 180 minus, what will be the measure of this angle? Measure, I mean the expression. What will be the expression for angle S? 180 minus, wake up class.
Half of angle A minus half of angle B.
Very good. Angle S will be 180 minus half angle A minus half angle D. What about angle Q?
Half of angle C, half of angle B. 180 minus half of angle C and half of angle B.
Correct. 180 minus half of angle B and half of angle C. So now vertically opposite angles are equal. So whatever you get here, the same thing here. This angle will be equal to this angle. This angle will be equal to this angle. So this angle, vertically opposite angles are equal. So you will get 180 minus half angle A minus half angle D. And here you will find this angle. This angle is equal to this angle. Vertically opposite angles are equal. So it will be 180 minus half angle B minus half angle C. So see here, 360 minus, you'll get the same thing. When you use these triangles, you can find the opposite angle straight away. If you use the other two triangles, you will have to find these two angles and then say vertically opposite angles are equal and get them inside. Numericals, we have done many. If the diagonals of a cyclic quadrilateral are diameters of the circle through the vertices of the quadrilateral, prove that it's a rectangle. If the diagonals of a cyclic quadrilateral, so the quadrilateral is a cyclic quadrilateral. That means there's a circle passing through the vertices of the quadrilateral. If the diagonals are the diameters of the cyclic quadrilateral are diameters of the circle passing through the vertices of the quadrilateral, prove that it's a rectangle. Okay, so since the statement talks about diameter also, so you'll have to draw a circle and show the cyclic quadrilateral. You'll have to prove it's a rectangle, so we're going to draw the quadrilateral in the shape of a rectangle. Now ABCD is the quadrilateral spoken about. ABCD is the quadrilateral and ABCD is a cyclic quadrilateral. It's given. Cyclic, you'll have to consider a cyclic quadrilateral and you'll have to prove it's a rectangle. So you can see ABCD looks like a rectangle. ABCD is the rectangle. Now it's not a rectangle. ABCD is now a quadrilateral. It's a cyclic quadrilateral. So we've also shown the circle. You don't have to always show the circle passing through the vertices for a cyclic quadrilateral. But here, since the diameters are mentioned, we have to show the circle. Only then you can show the diameters. For a cyclic quadrilateral, you don't have to always show the circle. But here, since the diameters are mentioned, only if you draw the circle passing through the vertices, you can show the diameters. If the diagonals of a cyclic quadrilateral, so ABCD is a cyclic quadrilateral, if the diagonals, so which are the diagonals? These are the diagonals. AC is a diagonal, BDs are the diagonal. Okay. Now these diagonals, if the diagonals of a cyclic quadrilateral are diameters of the circle, okay, so these are diameters, so that means this is O. This is O. Because the diameters, AC is the diagonal of the cyclic quadrilateral. AC is the diameter for the circle, so the center will lie on the diameter. BD is a diagonal. BD is a diagonal of the cyclic quadrilateral ABCD. It's the diameter to the circle. The line segments AC and BD are diagonals to the quadrilateral, diameters to the circle. Prove that ABCD is a rectangle. We need to prove that ABCD is a rectangle. Who can recall the definition of a rectangle? When is a quadrilateral a rectangle? What are the two conditions to be satisfied by a quadrilateral to be called a rectangle? The quadrilateral must be a parallelogram, and in the parallelogram, one angle should be a right angle. A parallelogram in which one angle is a right angle is a rectangle. So we need to prove two things. We need to prove that ABCD is a parallelogram. We need to prove that ABCD is a parallelogram. And also we need to prove that in ABCD, any one angle is a right angle. Any one angle is a right angle. If you can prove that ABCD is a parallelogram with one angle, right angle, see every other corner also can be a right angle, will be a right angle because it's a rectangle. But to prove it's a rectangle, you don't have to show that every corner is a right angle. You don't have to show that. So by the definition, you should prove that ABCD is a parallelogram with one angle 90 degrees. So ABCD is a rectangle. So ABCD is a rectangle. Now to prove that a quadrilateral is a parallelogram, there are many criteria. One of it is in a quadrilateral, if the diagonals bisect each other. In a quadrilateral, when the diagonals bisect each other, it is a parallelogram. Now tell me, is OA equal to OC? Is OA equal to OC? Am I audible and clear, children?
Yes, ma'am.
Yeah, is OA equal to OC? You're not sure? Tell me you're not sure. Is OA equal to OC? What is OA for the circle? What is AC for the circle? What is AC for the circle?
Diagonal, ma'am.
Which is the
What's the
radius.
Diameter, ma'am.
diameter? Yes. Yes, you're right, Sangamitra. What is OA for the circle?
Radius.
What is OC for the circle?
Radius, ma'am.
Then is OA equal to OC?
Yes, ma'am.
OA is equal to OC because radii of the circle. It's given BD is a diameter. We are not assuming. It is given that BD is a diagonal as BD is a diagonal of the quadrilateral. See, there are two figures here. One is the quadrilateral ABCD and the other is a circle with center O. So two figures. Now these line segments AC and BD, they're doing double roles. AC is the diagonal for the quadrilateral, diameter for the circle. BD, diagonal of the quadrilateral, diameter for the circle. AC, and so because they're diameters, they should intersect at O. Because they're diameters, they should intersect at O. That's how we get the center of the circle. See, we just don't mark O there. Because the diameters AC and BD will intersect at O, the center of the circle. OA is equal to OC radii. Is OB equal to OD? Is OB equal to OD? What happened? OB is a radius, right? Class, use the emoji, raise your hand. So I'm audible. Vasudevan, Pratiksha, Kanishka, Pranav, Deepika, Hitesh, Sangamitra, Tarun, Nikita, Satvika, and Tarun again. Okay, not Tarun again, Tarun. Okay. So children, you're all there at your desk. Please answer this question. Is OB the radius?
Yes.
And what about OD? OD is also the radius, right?
Yes.
So OB is equal to OD because the radii of the same circle. That means, see, the diagonals are cut into two equal halves. That means they bisect each other. If the diagonals bisect each other, the quadrilateral is a parallelogram. So what we say is OA is equal to OC. In the diagonal AC, OA is equal to OC. So the diagonal AC is cut into two equal halves, OA, OC. And the diagonal BD is also cut into two equal halves, OB and OD. OB and OD. So that means O is the midpoint. What do you mean by diagonals bisect each other? O is the midpoint of both the diagonals. For diagonal AC as well as diagonal BD, O is the midpoint. When the two diagonals have the same midpoint, that means they bisect each other. when the two diagonals have the same midpoint, that means they bisect each other. O is the midpoint of AC, O is also the midpoint of BD. That means the diagonals, they bisect each other. So in quadrilateral ABCD, the diagonals AC and BD bisect each other because they have the same midpoint O. And how do we know that O is the midpoint of both the diagonals? That is with the help of the circle. For the circle, AC is the diameter with O midpoint, meaning O center. For the circle, BD diameter, and O is the center of the circle. So O is the center of both AC and BD. O is the center of AC and BD that we get from the circle using the properties of a circle. And we apply that to the quadrilateral. So in quadrilateral ABCD, the diagonals AC and BD have the same midpoint O. That means they bisect each other. Therefore, ABCD is a parallelogram. And in the parallelogram, one angle is a right angle. Which angle? You can say this is 90, or you can say this is 90, or this is 90, or this is 90. How do you say this is 90? So circle. You can say I'll just take one diagonal. Let me take only one diagonal. ABCD. Let me take only one diagonal. So this is the diameter. So angle in a semicircle is a right angle. This angle is an angle in a semicircle. It's a right angle. Because BD is the diameter. So then this angle will be 90 degrees. Angle in a semicircle is a right angle. Or this angle is 90 degrees. Again, BD diameter. So this angle is a right angle. This angle is a right angle. Angle in a semicircle is a right angle. Or if you take the other diagonal, sorry. Same thing. Angle in a semicircle is a right angle. Angle B is 90, D is 90. So in fact, you can prove using this theorem that angle in a semicircle is the right angle. You can prove that all the four corners are right angles. So you say any one is a right angle. So in the parallelogram, one angle is a right angle, and hence ABCD is a rectangle. You can also use this theorem angle in a semicircle is a right angle and prove that all you should show separate figures like this. So one you connect AC and say this one and this one is 90. Then you connect BD. And say that this is 90, this is 90. So like this, all the four angles are 90 degrees. All the four angles are 90 degrees. So that means opposite. There's another criteria to show that a quadrilateral is a parallelogram. In a quadrilateral, when both the pairs of opposites are, when both pairs of opposite angles are equal, it's a parallelogram. So here opposite angles 90, 90, 90, 90. So it's a parallelogram. And one angle, in fact, every other angle is a right angle, but for the sake of definition, one angle is a right angle, so it's a rectangle. So you can do it in both the ways. Either use the property that in a quadrilateral, when the diagonals bisect each other, it is a parallelogram. And then one angle is a right angle, using angle in a semicircle is a right angle. Use these two and show that it's a rectangle. Or you can use only this theorem, angle in a semicircle is a right angle, and show that all the four angles are 90 degrees. In that case, what you'll have to do is when you show, in this case, where you show all angles are 90 degrees, you must say that ABCD is a parallelogram because opposite angles are equal. Opposite angles are equal, so it's a parallelogram. And in the parallelogram, one angle is a right angle, so it's a rectangle. Take a screenshot, children. If the non-parallel sides of a trapezium are equal, if the non-parallel sides of a trapezium are equal, that is, if the trapezium is an isosceles trapezium, then prove that it's cyclic. So we have to prove that an isosceles trapezium is cyclic. Prove that an isosceles trapezium, because non-parallel sides are equal. So that means it's an isosceles trapezium. Well, we need to prove that an isosceles trapezium is cyclic. So to prove that it's cyclic, one pair of opposite angles, one pair. If one pair of opposite angles is supplementary, the other pair also will be supplementary. So you don't have to prove both. So we'll prove that in this quadrilateral, one pair of opposite angles is 180 degrees. The sum of one pair of opposite angles is 180 degrees, or opposite angles are supplementary. So it is cyclic. Circle. Trapezium. You don't have to show the circle because there's nothing about diameter or something. No, you don't have to show the circle also. You can just take a trapezium like this. You can just take a trapezium like this. You don't have to show the circle also. Okay, so the isosceles trapezium is ABCD. The isosceles trapezium is ABCD. ABCD is the isosceles trapezium with AD equal to BC. Construction. Draw AM perpendicular to CD. Draw BN perpendicular to CD. Are you all listening?
Yes, ma'am.
Okay, so see. Two of us have already left the meeting. Who are they? Vasudevan, Pratiksha, Kanashika, Deepika, Hitesh, Sankamitra, Tarun. So Tarun has left. Nikita, Pranav's back. Okay. So construction should construction, draw AM and BN perpendicular to CD. Very simple proof. Very simple proof. Now, please help me prove that AMD is congruent to B and C. Please help me prove this. Triangle AMD. See, I'll tell you again. What is given is an isosceles trapezium with AD equal to BC. AD equal to BC. We'll have to show that ABCD is cyclic. Construction, draw AM and BN perpendicular to CD. Yeah, now what are the equalities available to show that these two triangles are congruent? Yes, children.
AM is equal to BN since they are the heights.
AM is equal to BN. How are they equal?
Height.
Height. Huh? Okay. Okay, correct. Then
AD is equal to BC since it's mentioned that it's an isosceles trapezium.
correct. Next.
And angle AMD is equal to angle BNC. We construct it. A perpendicular.
Construction perpendicular. Correct. So what's the congruence criterion?
RHS.
RHS. By RHS rule, the two triangles are congruent to each other. By construction, we have angle 1 is equal to angle 2, 90 degrees. For H, that is right angle. For H, AD is equal to BC. AD hypotenuse, BC hypotenuse, they are equal. Side, AM is equal to BN because AB and CD are parallel lines. The distance, the perpendicular distance between two parallel lines is the same everywhere. Now, if this is a tabletop, if this is a tabletop, okay, a rectangular tabletop, opposite sides are parallel. If you use a scale and measure this distance, the perpendicular distance, supposing it is 50 centimeters, it will be 50 centimeters everywhere. The perpendicular distance, not a distance like this. Distance in maths is always perpendicular distance. So the perpendicular distance between two parallel lines, is the same everywhere. So AM will be equal to BN because perpendicular distance, AM is perpendicular. That is AM and BN are perpendicular, represent the perpendicular distance between the parallel lines AB and CD. These are parallel because it's a trapezium. So these two are the distances between two parallel lines and they'll be the same everywhere. So AM is equal to BN. So RHS congruence rule, the two triangles are congruent. CPCTC, this angle is equal to this angle. CPCTC, this angle is equal to this angle. So now these two angles are equal. But we know that this angle plus this angle is 180 because co-interior angle is supplementary. Co-interior angle, let me call this angle A, this one angle D, and this one angle C. Okay, let me call this angle A, angle D, and angle C. Now, the result we got by congruency is angle D is equal to angle C. Angle D is equal to angle C. Okay, but angle D plus angle A is 180. See, now we need to introduce 180 degrees because to prove it's cyclic, we need to show that one pair of opposite angles is supplementary. So from congruency, we have angle D is equal to angle C. Next, angle D plus angle A is 180 because parallel lines co-interior angles are supplementary. Parallel line, transversal, parallel line. Co-interior angles are supplementary. Parallel lines, transversal. Co-interior angles are supplementary. But we know this angle D is equal to angle C. So replace instead of D, say angle C plus angle A is equal to 180. Because D is equal to C, D is equal to C. So take away D and say C. Angle C plus angle A is 180. So C plus A is 180, meaning opposite angles are supplementary. Therefore, ABCD is cyclic. So prove that these two triangles are congruent to each other. CPCTC, angle D is equal to angle C. So till there it should be easy. Then somehow get 180 degrees. Get one. You can also say that angle. You can also say that angle C plus B is 180. C, angle C plus angle B. Angle C plus angle B is 180. What if you write that angle C plus angle B is 180? But angle C can be replaced with angle D because they're equal. We proved now through congruency. So we'll get D plus B is equal to 180. Write it again. You can also see the result we got through congruency is angle C is equal to angle D. Keep this in mind. Now angle B plus angle C is 180. Co-interior angles are supplementary. Now C and D are equal. So take away C. Angle B plus angle D is equal to 180. Angle B plus D is 180. B plus D is 180 meaning opposite angles are supplementary. So it's cyclic. ABCD is cyclic. Take a screenshot, children. We just have one more to go. Please wait. Done with this?
Yes, ma'am.
Okay. Okay, so here in this figure, we'll have to show that ACP, where is ACP? ACP. It's marked here. You can see it's marked there. ACP, this one. ACP is equal to QCD. QCD. It's marked here. We need to show that these two angles are equal. We need to show that these two angles are equal. Let me number them. So I'll mark some angles here. Is angle 1 equal to angle 3? Is 1 equal to angle 3? Name angle 1, children. Name angle 1. Angle. What is this? How do you name this angle? Angle. Angle ABP. And this angle, angle 3, angle ACP. ABP, ACP. Angle 1 and angle 3 are angles ABP and ACP. They are made by the same. So angle ABP and angle ACP are two angles subtended by the same arc AP. Subtended by the same arc AP at the points B and D on the B and C on the circumference. Angles in the same segment of a circle are equal. See, there is a circle, the first circle. So there's one angle like this. There's another angle like this. A, B, sorry, this is P, sorry, P, A, and this is C. This is the arc. This is the arc. AP is the arc. AP makes ABP and ACP. ACP. So angle 1 is equal to angle 1 is equal to angle 3. Angles in the same segment of a circle are equal. I'll just write same segment. I don't have the proof for this now. Yeah. So you'll have to take a screenshot of this. Angle 1 is equal to angle 3. I'll just write same segment. Angles in the same segment. The same segment of a circle are equal. Similarly, angle 2 can be called angle DBQ. And this is angle DCQ. So from the name you can make out DBQ is an angle subtended by arc DQ at the point B, and DCQ is an angle subtended by arc DQ at the point C. DBQ, DCQ. The arc is DQ. Look at the figure. DQ is the arc. DBQ, DCQ. So angle 2 and angle 4 are two angles subtended by the same arc DQ at the points B and C on the circumference. They're equal. Angle 2 is equal to angle 4. Same reason, angles in the same segment of a circle are equal. This arc AP subtends angle 1 and 2. This arc DQ subtends angle 3 and 4. But angle 1 and 2 are vertically opposite angles. Angle 1 is equal to angle 2. Vertically opposite angles are equal. It's given there. It's given that. I didn't read the question. They're straight lines here. Two line segments ABD and PBQ. ABD and CBQ. PBQ, sorry. PBQ. So these are two line segments. They intersect like this, and vertically opposite angles are equal. Angle 1 is equal to angle 2. See, it's given here. ABD and PBQ. ABD and PBQ. ABD, PBQ. They are two line segments. They intersect at B. So vertically opposite angles are equal. Angle 1 is equal to angle 2. Vertically opposite angles are equal. 1 is equal to 3. 2 is equal to 4. But 1 and 2 are equal. So 3 and 4 are equal. 3 is equal to 4. And this is angle 3. This is angle 4. So like this, we prove that angle 3 is equal to angle 4. Angle 1 is equal to angle 3. Angles in the same segment of a circle are equal. 2 is equal to 4. Same in the other circle. In the other circle, angles in the same segment of the circle are equal. But 1 and 2 are equal angles vertically of their angle 1 is in one circle, 2 is in the other circle. But they're equal because they're vertically opposite angles. So from these three results, if 1 is equal to 2, if 1 is equal to 2, then 3 is equal to 4. So we proved that angle 3 is equal to angle 4. Since I don't have the answer slide, please take a screenshot of this one. Done, children? Okay. Yeah, this one. Take a screenshot. We'll do this one and wind up the session for today. The rest of the questions in this exercise are numericals. The proofs we have completed now. With this, we'll complete. So we are given that ABC and ADC, ABC and ADC are two right triangles with common hypotenuse AC. ABC and ADC are two right triangles with common hypotenuse AC. So now the question is, do the triangles lie on the same side of the hypotenuse or on the opposite sides of the hypotenuse? Do the two right triangles lie on the same side of the hypotenuse or opposite sides of the hypotenuse? So we'll have to consider both the situations. So what you see here, case 1 is two right triangles, ABC. I'll show them separately. AC is the hypotenuse. it's given AC is the hypotenuse. That means ABC, B is 90 degrees because AC is the hypotenuse is given. AC is the hypotenuse is given. So that means angle B is 90. The other one is ADC. There also, I'm drawing it separately, but they're not two separate triangles. AC is the common hypotenuse. AC is the common hypotenuse. They're not two different triangles. AC is the hypotenuse. ADC, this is 90. Because AC is the hypotenuse, D is 90 degrees. Opposite of the hypotenuse. Children, am I audible?
Yes, ma'am.
Yes, ma'am.
Sometime back, was I audible?
Yeah, ma'am.
No, I don't know. I thought I lost my network. Okay. All right. So we have two right triangles. ABC, ABC and ADC with a common hypotenuse AC. So the figures can be like this. AC is the common hypotenuse. AC is the common hypotenuse. It can be like this ABC and ADC. Like this ABC, ADC. See here, this is 90, this is 90. Common hypotenuse. AC is the common hypotenuse. ABC, ADC. Correct? Or with AC as the hypotenuse, you can have one right triangle here above AC and the other triangle like this below AC. AC, AC, ABC, ADC. If you can understand this, if you say this is fine, I can go ahead. Don't look at these figures. Don't look at these figures. Please tell me if you understand this. This is the hypotenuse, common hypotenuse AC. And the two triangles ABC, ADC, right triangles on the same side of AC. Here on opposite sides of AC, ABC, ADC on opposite sides of AC. Do we understand these two figures? This one and this one? Yes or no, children?
Yes, ma'am.
Why is sluggish? Yes, ma'am. All right. So this is what you see here. This is what you see here, the first figure, where the two triangles ABD and ACD lie on the same side of AC. And here in figure 2, they lie on opposite sides of AC. You can just drag this figure into the circle here. I'll tell you why we draw a circle. See, this is what you see here, and this is what you see here. Dotted lines are construction. Okay. So ABC and ADC are two right triangles with a common hypotenuse AC. Prove that CAD is equal to CBD. Prove that CAD is equal to CBD. Now what we're going to do is we're going to show that in both the cases, a circle can be drawn passing through the four vertices A, B, C, and D. See here we only have this figure. AC is the hypotenuse. So we prove that a circle can be drawn. Later we draw the circle. We prove that a circle can be drawn passing through all the four vertices. We prove that a circle can be drawn passing through all the four vertices. And then we draw the circle. Here also we have only this figure. ABD like this and ACD like this, like this. We prove that you can draw a circle passing through the four vertices. And then we draw that circle. And joining BD and BD here and BD here, construction. Joining BD here and BD here is the construction. I'll explain all that. Okay. So how do we show that a circle can be drawn passing through the four vertices A, C, D, and B? So go back to that theorem, which, which I think I told you at the start of this chapter, circles. When a line segment subtends equal angles at 2 points on the same side of it, then the 4 points are concyclic. So you can see here the line segment AC. The line segment AC subtends equal angles at the points B and D. At the points B and D, it subtends equal angles. Here, ABC is equal to ADC. ADC because both equal to 90 degrees. The line segment AC makes ABC, ADC, two angles, two equal angles at 2 points B and D on the same side of it. So if these conditions are satisfied, then the 4 points are concyclic. And yes, they are satisfied because we have a line segment AC. And this line segment AC on the same side of it, it subtends two angles, ABD and ADC. Both are made by AC. ABC, ADC. Am I audible and clear, children?
Yes, ma'am.
Okay. So it makes ABD and ABD, ABC is made by AC. AC is here. Join ABC. It's made by the line segment AC at the point B. And the same line segment AC, ADC. I've told you, join the ends of the line segment to that point. So since the line segment AC subtends equal angles at the points B and D, lying on the same side of it, both B and D are on the same side of AC. Equal angles because both are 90 degrees. The 4 points are said to be concyclic. That means you can draw a circle passing through all the 4 points. So if you can draw a circle passing through all the 4 points, you can use some property of a circle. We have to show that CAD is equal to CBD. See here, made by the same arc CD at the points A and B. So CAD, see here CAD is this angle. CAD is this angle. CBD. Since this is not connected, we join BD. So CAD is equal to CBD. Yeah, true, because angles in the same segment of a circle are equal. There are two angles made by the same arc CD. CAD, CBD. Same arc CD at the points A and B on the circumference. So we proved that CAD is equal to CBD. This figure is where the two right triangles are on the same side of the hypotenuse. First, you must use this theorem and show that a circle can be drawn passing through A, B, C, and D. After drawing the circle, identify the angle CAD, this one. Identify the angle CBD. CBD, you can't see the angle, so you have to join this. Only then you can see the angle CBD, this one. And why is CAD equal to CBD? Because now that you can draw a circle, now CAD and CBD, they're angles in the same segment of a circle, and hence they're equal. In the second figure where the two, ignore this, okay, this we join later, ignore this. See the figure without that dotted line, BD. So here ABC and ADC, they lie on the opposite sides of AC. And here, why is that? How is that you can draw a circle passing through the vertices? Because opposite angles are supplementary. In the quadrilateral ABCD, opposite angles are supplementary. B plus D is 180. That means it's a cyclic quadrilateral. In both the cases, in the two cases, we use different reasons. The reasons are different. Why a circle can be drawn passing through the four vertices, the reasons are different. So in the second case, angle B plus angle D is 180. Angle B plus angle D is 180 because both are right. Angle B is 90 degrees, D is 90 degrees in the two right triangles. So in quadrilateral ABCD, opposite angles are supplementary. In quadrilateral ABCD, opposite angles are supplementary. So ABCD is cyclic. So you can draw a circle passing through the four vertices. And now looking out for CAD and CBD. CAD and CBD. CAD, it's here. CBD you can't make out. So we join to make out the triangle. So now you see CAD is equal to CBD because angles in the same segment of a circle are equal. Angles in the same segment of a circle are equal. CAD is equal to CBD because angles in the same segment of a circle are equal. They're made by the same arc CD at the points A and B on the circumference. So they're equal. That's what we had to prove. Prove that CAD is equal to CBD. So case 1 is where the right triangles lie on the same side of the hypotenuse. Case 2 is where the right triangles lie on the opposite sides of the hypotenuse. And to prove that these two angles are equal, we use this property. Angles in the same segment of a circle are equal in both the cases. Angles in the same segment of a circle are equal. Why we join BD? Why we join BD in both? In both the figures, we join BD because we're not able to make out this angle CBD. Angle CBD, but only if you join BD, you can make out that angle CBD. So we join BD. And the angles are equal because in both the cases, the angles in the same segment of a circle are equal. And to use this reason, there should be a circle. And for the circle, we'll have to show that the quadrilaterals. In the first case, AC, DB or AB, DC. And here ABCD, they're cyclic. Only if you show that they are cyclic or if you show that a circle can be drawn passing through the vertices, you get a circle. So here the property is the line segment AC subtends equal angles at the points B and D lying on the same side of it. Then the points A, B, D and C are cyclic. Concyclic, sorry. The points are concyclic. So you can draw a circle passing through the four vertices. In this case, we say opposite angles are supplementary. In quadrilateral ABCD, opposite angles are supplementary. So it is cyclic. Take a screenshot, children. Okay, so with this class, we come to the end of your classes for 9th standard. Your exams are, most of you are starting your exams from tomorrow or from this week. Any help regarding your preparations, please reach out to me. I'll help you, if possible, call me. If you want to call me and get your doubts clarified, you can call me. Or if you want to share the question on WhatsApp, I'll work it out and share the picture, whatever is your convenience. So any help, reach out to me. I've shared the videos. Polynomials were completed in term 1 itself. And sometime back, I'd also shared the videos, the YouTube videos on polynomials. So in polynomials, if you have any doubts regarding factorizing using factor theorem or anything else from that chapter, please reach out to me. So in general, any doubts while preparing for your exams, please don't hesitate to text me or call me anytime, literally anytime.
Okay, ma'am.
Yeah. Let me see how many of you are there at the end of the session. So we have Vasudevan. All of you lower your hands. Lower your hands, class. Okay, so we have Deepika. So we have these patient children. At the end of the session, Deepika, Kanishka, Vasudevan, Nikita, Pranav, Sangamitra, and Satvika. The others were hungry, so they left the meeting. All right, children. So that's it for today's class. And as I told you, this is the last class for 9th standard. Thank you so much. I hope all the classes were useful. And I hope you continue to support my classes for 10th standard. Thank you so much, children. All the best for your preparation.
Thank you, ma'am.
Do well. Yeah.
Thank you.
Thank you. Thank you. Yeah.
Thank you, ma'am.
Good luck, children. Thank you. Good luck.